Hey guys, here's section 5.3, day 2. We're graphing polynomial functions still. So this time, instead of the polynomials being given to you in factored form, which obviously makes graphing them a little bit easier, they're not going to be in factored form, which means you're going to have to find all of those x-intercepts on your own first. So you're going to have to set all of these equations equal to 0 and solve. All right, so here we go. So it says, sketch the graph of the given polynomial function. So again, if I want to sketch it, I need the degree, I need the leading coefficient sign, and I got to determine that end behavior along with my x-intercepts. All right, so let's find our x-intercepts. So let's set it equal to 0 and solve. Well, if I'm going to solve this by factoring, the first thing we always look for is a GCF. So what does a negative 2x to the third, a 5x squared, and a 12x have in common? In this case, they only have an x in common. But because there's leading with a negative number, we're going to pull the negative sign out too. So we're going to pull out a negative x, which is going to leave us with 2x squared, a negative 5x now, and a negative 12. Well, now I'm going to look to see if this factors again. So bring down your negative x, and let's see if we can factor this again. Well, it looks like a normal quadratic equation, a degree 2 that we would factor. So what times what gets me 2x squared? Only a 2x and an x. Whatever I put here and whatever I put here better multiply to negative 12, and then my rainbows better go to a negative 5x. So I know for factors that multiply to 12, I have 6 and 2, 4 and 3, 12 and 1. I'm going to put a 4 here because that'll get me 8 x's. And I'm going to put a 3 here because that'll get me 3 x's. And 8 and 3 should be able to go to negative 5. I just got to make sure my signs can work. So I'm going to put a minus here and a plus there. And that gets me 3 x's and negative 8 x's, and it still multiplies to a negative 12. So that's good. So now we set all of our factors equal to 0 and solve. So if I set negative x equal to 0 and solve, divide by negative 1, and you get x equals 0. That's one of your x-intercepts. Now remember, if this is a degree 3 polynomial, it should have at most 3 x-intercepts. So I should be able to find 3 numbers. All right, if I set 2x plus 3 equal to 0 and solve, minus 3, and divide by 2. And x equals negative 3 halves, or negative 1.5 if it makes it easier to graph that on your x-axis. And then the last one, if x minus 4 gets set equal to 0, then x would equal 4. And those are my 1, 2, 3 x-intercepts to my degree 3 polynomial. So now let's plot them. Okay, I have an x-intercept at 0. I have an x-intercept at negative 1.5, negative 3 halves, which is right there. And I have one at 4. So these are the only 3 spots where your graph should cross over or touch the x-axis. All right, now in order to fill the graph in, I need the degree of my polynomial and the sign of the leading coefficient. Well, the one good thing about it being in multiplied out form, in standard form, not factored form, is that I can see that the degree of this polynomial is 3. The highest exponent on a variable is 3. So that means it's degree 3, which is odd. And the sign of the leading coefficient, well, the leading coefficient is negative 2, so it's a negative leading coefficient. All right, what did we say the end behavior has to be for an odd degree graph? The end behavior has to be different, right? One end is up and one end is down. Well, which end is up and which end is down depends on the sign of the leading coefficient. When the leading coefficient is negative, it's going to be up on the left side of the graph and down on the right side of the graph. So to the left of my last x-intercept, my graph has to end up. And to the right of my last x-intercept, my graph has to end down. Now again, I told you yesterday, if that confuses you, plug a number to the right of your last x-intercept in. So like 5 or 6 or 7. If you plug it into this equation and a negative number comes out, then you know the graph ends down here. If a positive number comes out, you know the graph ends up here. And then you can plug a number in to the left of your last x-intercept. So if this is negative 1.5, you could plug in negative 2, negative 3, negative 4, negative 5. Plug that into that equation. If a positive number comes out, you know the graph ends up here. If a negative number comes out, you know the graph ends down here. All right, well now the graph should fill itself in. So I know I have to end up and I have to head towards that x-intercept. So I'm going to do that. So end up, and let's head towards our first x-intercept. What is your graph eventually going to have to do to head towards the next x-intercept? It has to turn. So at some point, you've got to turn. I'm going to turn, I'm going to cross over, and then again, what's my graph eventually going to have to do to head towards the next x-intercept? It's going to have to cross. So now I'm going to turn, it's going to have to turn, and then it's going to head towards it, cross, and then stay down. As long as I have no more x-intercepts to turn towards, I should stay down below the x-axis here. And again, notice my graph only crosses or touches the x-axis at these 3 dots. All right, perfect. Okay, well, then they ask you the end behavior. I told you sometimes they make you talk a little fancy. So look what they're saying. This is how we actually physically describe the end behavior of the graph. What's going on at each end of the graph. As x goes to positive infinity, well, remember, x lives on this axis, and y, or f of x, as we call him now, lives on the y-axis. So as x goes towards positive infinity, so as x gets bigger, as x goes towards positive infinity, right? You plug this number in, that number comes out. You plug this number in, that number down here comes out. That's where the graph is going. So those are the y values that are coming out of this function as x gets bigger and bigger. So as x gets bigger and bigger and bigger and bigger and heads towards infinity, what's the y value? What's the f of x value heading towards? It's heading towards negative infinity because the graph is ending down. All right, and then it says, well, as x goes to negative infinity, right? So as x goes to negative infinity and gets smaller and smaller and smaller. As x goes to negative infinity, what's the f of x, the y value doing? Well, as x gets smaller and smaller and smaller, this x makes that y value come out or f of x come out. This x is going to make that y value or f of x come out. So as x goes to negative infinity, what's f of x doing? What's f of x heading towards? It's heading towards positive infinity. And on an odd degree graph, the end behavior should be different. One end should head towards negative infinity, and one end should head towards positive infinity. All right, that takes some getting used to. All right, let's try this one. Now it asks you to graph this polynomial function. Well, again, it's a degree 4, so it could have 4 x-intercepts, okay? That also means it's an even degree function, so you can already start predicting his end behavior, whether they'll be different or the same and whatnot. All right, well, let's get his x-intercept. So let's set it equal to 0. Okay, well, the first thing I would normally look for is a GCF, but x to the 4th, 5x squared and 4, they don't have a GCF. So you're kind of like, how am I going to factor that? That's a degree 4. It's not a quadratic. But if you remember from section 5.5, when we were solving all those polynomials by different kinds of factoring, this is a degree 4 polynomial that acts like a quadratic. It's an even degree. And that term is half of his term. That's a 4 and that's a 2. So if you tried to factor this, it will factor just like a quadratic in the sense that whatever I put here and here has to multiply to x to the 4th. Whatever I put here and here has to multiply to 4. And then my rainbows have to add up to those negative 5x squares. Well, think about it. What times what could you use to multiply to x to the 4th and still allow you to get those x squared terms in the middle? An x squared and an x squared. They multiply to an x to the 4th. And now my rainbows will add up to so many x squareds. All right, well, what numbers do you know multiply to 4? A 2 and a 2 or a 4 and a 1? It looks like it's a 4 and a 1 who are going to work this time. And now what signs do they have to be to add up to negative 5x squared and positive 4? Well, to multiply to a positive and add up to a negative, I need negative, negative. So now you have factored it. You can set each one of these factors equal to 0 and solve using square roots. Or if you notice, both of these are the difference of 2 perfect squares. So both of those can factor again. So now this will factor to an x plus 2 and an x minus 2. This will factor to an x plus 1 and an x minus 1. So now when you set all your factors equal to 0 and solve, you're going to get x equals negative 2, x equals 2, x equals negative 1, and x equals 1, just to save us a little bit of time. So now you have 1, 2, 3, 4 x-intercepts to this degree 4 polynomial. That's perfect. All right, well, my x-intercepts are pretty close, so I'm going to space them out a little bit. Okay, so now your graph will cross the x-axis or touch it at these 4 points. So -2 and +2, -1 and +1. Those are the only spots where your graph should be touching or crossing the x-axis. All right, let's get our end behavior. This is a degree 4 polynomial with a leading coefficient that is +1. Well, what's the end behavior for an even degree polynomial graph have to be? Well, even degree, the end behavior has to be the same, both up or both down. Well, if the leading coefficient is positive, which one is it? Both up. So to the right of my last x-intercept, my graph has to end up. To the left of my last x-intercept, the graph has to end up. And now we're gonna head towards it and let the graph fill itself in. So I'm gonna end up, and I'm gonna head towards the first x-intercept. I cross over. What's the graph gonna have to do to head towards the next x-intercept? Eventually it's gotta turn and head back up. It crosses over. Eventually what's it gonna have to do? It's gonna have to turn and head towards the next x-intercept. It's gonna cross over and eventually it's gonna have to turn and head towards the next x-intercept, and then we said end up, and I am out of x-intercepts. And that's what your graph should look like. And again, it might not look exactly like mine, but we should have the same x-intercepts, and our graph should be positive in the same spots, and it should be negative in the same spots. All right, let's fill in our end behavior. So as x goes to positive infinity, so as x goes to positive infinity, what is f of x, y heading towards? Well, as x got bigger, what was the end of the graph doing? It was going up. So y is heading towards positive infinity. Well, look at the left side. As x goes to negative infinity, as x gets smaller and smaller and smaller and heads towards negative infinity, what is the y value doing at this end of the graph? It's going up, so who is y heading towards? Positive infinity. And notice on an even degree graph, the end behavior should be the same. So they should head towards the same infinity. All right, let's try another one. Okay, same thing. If I'm gonna graph this, I have to find the x-intercepts. So I'm gonna set it equal to 0 and solve. First, I'm gonna look for a GCF, but an x to the 4th, an x squared, and an 18 don't have one. So I don't have a GCF, but I don't like to factor when my leading sign is negative, so I'm at least gonna pull out the negative sign. So that's gonna leave me with a positive x to the 4th, a negative 11x squared now, a positive 18, and it's still equal to 0. All right, well, again, this is one of those degree 4s that we can factor like a quadratic. So what times what gets me x to the 4th and still allows me to get those x squareds in my rainbows, an x squared and an x squared. And now I'm looking for numbers that multiply to positive 18, and my rainbows have to add up to negative 11x squareds. Well, that should be a negative 9 and a negative 2. Okay, now this is the difference of two perfect squares. So he can definitely factor again. This is not the difference of two squares, so he has to stay, and we're gonna have to use square roots to solve him. All right, so we're gonna get negative, factor him again. He says that stays. All right, so this becomes an x plus 3 and an x minus 3. So again, they really expect you to be kind of factoring wizards by now, right? All right, so if you set all your factors equal to 0, if I set negative 1 equal to 0 and solve, well, that doesn't make any sense. Negative 1 does not equal 0, and there's no variable to solve for. So I don't get an answer from that factor. If I set x plus 3 equal to 0 and solve, I get x equals negative 3. That's one of my x-intercepts. If I set x minus 3 equal to 0 and solve, I get x equals positive 3. So that's one of my x-intercepts. So now, if I set x squared minus 2 equal to 0 and solve, I'm going to add my 2 over, get my x squared alone, and then I'm going to square root both sides. But remember, this is a degree 2 equation. You should get 2 answers. So when you unsquare a square, it creates 2 actual answers. So we get x equals plus or minus the positive or the negative square root of 2. And then just to make graphing easier, if you ask your calculator what is the square root of 2, it's about plus or minus 1.4. Just so you know where to put them on your number line or your x-axis. All right, so now we have 1, 2, 3, 4 answers to my degree 4 polynomial equation. So those are my 4 x-intercepts. So let's put them on the graph. All right, so I have an x-intercept at -3. I have an x-intercept at +3. I have an x-intercept at positive 1.4 and negative 1.4. All right, those are the only spots where your graph should be crossing over the x-axis. All right, now I need my degree, which is 4, and the sign of my leading coefficient, which was -1. So what does an even degree polynomial end behavior have to be? It's got to be the same, so either both up or both down. If the leading coefficient is negative, it's got to be both down. So to the left of your last x-intercept, the graph has to end down. To the right of your last x-intercept, the graph has to end down. All right, now let's go and fill the graph in. So let's end down. And let's head towards our first x-intercept. We cross over. What do we eventually have to do to get to the next x-intercept? We have to turn. We cross over. What do I eventually have to do to go to the next x-intercept? I got to turn. And then when I cross over, what do I got to do to head to the next one? I got to turn and I cross over. I got no more dots to head towards, and my graph says I should be ending down at this point. And there is your graph. So again, it's going to look different, but as long as I call them peaks and valleys are the same, like I'm up here in between these x's, I'm up here in between these x's, I'm down here, and I'm down here. Remember, all this graph is showing us is that these x values make a negative y value come out, these x values make a positive y, these x values make a negative y, these x values make a positive y come out, and these x values make a negative y value come out. Okay, the end behavior. The fancy talk, right? So let's follow it. As x goes to positive infinity, so as x goes to positive infinity, right? What is this end of the graph doing? What is y doing or f of x doing? It's going down. So it's heading towards negative infinity. And again, if it's even, it should have the same end behavior. Well, as x goes to negative infinity, so as x gets smaller and smaller and smaller and heads to negative infinity, what's this end of the graph doing? It's going down, 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 down. So who is f of x, the y value heading towards? Negative infinity as well. All right, last one. Okay, well, if I want to graph this degree 3 polynomial function, I have to find his x-intercepts. So let's set it equal to 0 and solve. Well, the first thing I would do is look for a GCF. X cubed, 3x squared, 16x, 48, they don't have one. And it doesn't leave with a negative, so I don't have to pull a negative out. So it's kind of like, well, how am I going to factor that? He's got 4 terms, no GCF. Well, remember, if he's got 4 terms, then he might factor by grouping. So let's try to factor it by grouping. Group the first 2, group the second 2. All right, and now we pull out individual GCFs from the first group and the second group. So what's the GCF between an x cubed and a 3x squared? Excuse me, an x squared. Take it out, and that leaves me with x minus 3. Now remember, when you go to factor by grouping, you have to pull the leading sign out of that second group. So pull out the minus, and now what does a 16x and a 48 have in common? They actually have a 16. So if I take that out, what's negative 16 times who gets me back to negative 16x? X. Negative 16 times who gets me back to positive 48? Negative 3. Ooh. Negative 3. So factor by grouping worked, because remember, factor by grouping only works if you end up with that matching factor. So one factor is x minus 3, the one that matched, and the other factor is who we pulled out, x squared minus 16. Now you could set them equal to 0 and solve right now, and you could use square roots for this one, or you should recognize that he's the difference of 2 squares, and he'll factor again really, really quickly. So I get x minus 3 still, and then he'll factor to x plus 4 and x minus 4. And then you set all your factors equal to 0, and you get 3, negative 4, and 4 as your 3 x-intercepts. They are your 3 roots, your 3 zeros, your 3 x-intercepts to this degree 3 polynomial. So let's plot them. Okay, well I got what? Positive 3, negative 4, and positive 4. That's going to be a little tight. There's going to be a quick turn there. All right, so here we go. So now what's our end behavior? The end behavior, this is a degree 3. So it's odd, and the leading coefficient was positive 1. So what does the end behavior of an odd degree graph have to be? It's got to be different. So one end has to be up, and one end has to be down. right? Which end is up and which end is down though? If the leading coefficient is positive, then it's going to be up on the right, the positive side, and down on the left. So to the right of your last x-intercept, your graph has to end up. To the left of your last x-intercept, your graph has to end down. And then we just let the graph fill itself in. So I'm going to end down, and I'm going to head towards my first dot. I'm going to cross over, and then my next one is all the way over there. So eventually, I'm going to have to turn and head towards my next x-intercept. I'm going to cross over, and then rather quickly, maybe, we don't really know where, but I'm going to have to turn at some point and head back up to the next one. So head back up, and then it ends up. And then that would be your graph. So they're not going to be the prettiest pictures, and they're all going to look different. Mine is going to look different than yours, but we should be negative and positive in the exact same spots, and we should have the exact same x-intercepts. But our peaks and our valleys might look a little bit different as to how high or low they go. All right, let's fill in the fancy talk. As the end behavior, as x goes to positive infinity, as x goes to infinity, what's f of x doing? What's y doing? He's going up, so he's heading to infinity. As x goes to negative infinity, what is f of x or y doing? Now this end is heading down, so who's he heading towards? Negative infinity. Okay. All right, guys, good luck. Graphing, like I said, it takes some time, but when you ever get stuck, the one thing you could do is you could plug in when x is 1 into this equation, and whatever y value comes out, that creates an ordered pair that your graph has to pass through. So if you want to create more points that your graph has to pass through, then just plug these x's into the equation and see what y value comes out. All right, good luck, guys.